All right, welcome to another IAEI News Live. My name is Thomas Dimitrovich. This is a recorded session. I'm on the road, and as you could tell, I'm obviously in a hotel room. But I want to do a session. I want to do today's session on overcurrent protection. So I'm going to focus on circuit breaker basics first. And I think maybe another recorded session that I'll do, or maybe I'll do it live, we'll talk fuses in the future. And then maybe we'll get into relays, right? So that's all overcurrent protection. But today on IAEI News Live, I want to talk about overcurrent protection and circuit breaker basics. This is a recorded session, and it all starts now. All right, welcome back, everybody. So, man, there's a lot going on in the electrical industry right now. I'm out at a IEEE Institute of Electrical Electronics Engineers. It's a petroleum and chemical group that gets together on an annual basis every year. We have a big conference, and we talk about a lot of different things. But and next week is the IAEI Western Section meeting, and I hope you're as excited about it as I am, and I'm hoping to see every one of you in West Virginia at the Western Section meeting in Oglebay Park. So we are going to have we're going to have a blast. We have a great program lined up, and I trust that, man, we're going to learn a lot. We have a lot of great industry experts. One of the things you'll recognize at all of our IAEI events, we have a lot of industry partners, that experts in the industry that travel from miles around to come and partake in the festivities and enjoy talking about electrical safety. So I'm hoping to see you at the Western Section. Okay, so as you know, and as you hopefully know, NFPA 70 public inputs closed last week on the 7th. I hope you were able to get your public inputs in. I know I've got a bunch of them in, and there's a lot of work going on out there with the next edition of the code. Now, if you're interested in knowing where you find all the information, what I will say, if you drop out to the NFPA's webpage, and what I did here was I went to, and I'm just going to retype it, www.nfpa.org/70NEXT. It takes you straight to the next edition tab. This tab, this tab right in here, it says next edition. That tab right there, you have current and prior editions, you have the next edition, you have the technical committee, you can ask a technical question, any news, etc. But we're on the next edition, and you'll notice that the first draft public input closing date was September 7th, 2023. And just in case you didn't realize, well, you probably realize this now, it closed at 5 o'clock, not at 11:59. So I think that may have caught a few people. I know it did catch me. I for some reason, I saw September 7th, 2023, thinking 11:59 p.m. and it's not. It was 5 o'clock p.m. So there were some items that I was looking at trying to improve the NEC and getting in, but I wasn't able to get mine in. So you know what? I wait 3 years. That's okay. So, the NEC is like a fine wine. It just gets better with time. That's all. So in any case, this shows you that there is no, this is where you'll go to see when they actually publish the public inputs, the information for Terra on what the public inputs were, this is where you'll find them. Now, committee members are going to get all of those files and all of the information in from NFPA, and we are going to start task group work. So if you're interested in getting engaged with the NFPA process, then what you're going to want to do is understand what task groups are being formed, and then you can be guests. And you may not be able to speak, you may not be able to contribute unless you ask the chair for permission to present. The chair will give you a period of time. Usually it's about 5 minutes. And you'll be able to share whatever it is that you need with the panel, especially if you have a public input. It's great, in my opinion. It's great to engage with the individuals, the code making panel members, presenting to them. Now the task group work will be virtual, but now the first draft meeting is going to be an in-person meeting, and it's going to be in Charleston, South Carolina. If you want to know how to get to that information, if you scroll down, you will see there's the correlating committee, there's code making panel 1 and 2 and 3, and you'll see data. So I'm on panel 2, so let's take a look at panel 2. We can hit view, and here's the letter that went out from Jeff Sargent on panel 2 to all the panel 2 members. It's going to be at the Charleston Marriott at 170 Lockwood Boulevard. Now here's my thought process on this, and I'll tell you what, I lucked out. If you know me, you know that I rarely book my hotels in advance. I don't know why. I think I travel so much that sometimes I forget, and that's my excuse. But in any case, the moment this came out, you'll see that there's a booking link, and I booked my room, thank goodness, because I'm telling you, these hotel blocks fill up fast. So please, if you're going, get your hotel reservations now. Don't wait. And okay, so here's this complete schedule right here. So you have January 15th to 26th. So the first week is Monday the 15th through Saturday the 20th. CMP2 is meeting the first week. So is CMP 16, 9, 8, and 13, 6, 11, and 18. And you'll notice that some of these panels only meet for 2 or 3 days. It's typically based upon the volume of public inputs that they're typically getting. So obviously when they set this schedule up, they did not know how many public inputs that each panel was going to get. But suffice it to say, that's where they're at. So that's where we're at. I just at least wanted to bring that up with you before I got into overcurrent protection and circuit breakers, and primarily because, when we talk about code requirements, we have to understand that the NEC is on a journey and it's going to change. So please be mindful and be engaged. All right. So even though your jurisdiction may enforce the 2017 code, that doesn't mean you should not be looking at the 2020 or the 2023 or the 2026 as it's being developed, because we learn. Remember, nobody can take what's up here, right? I can take your house, I can take your car, the bank can take anything, but they can't take what you know. So learn and be a sponge, and you will be able to use that information. So the first step in our journey. Now, I'm going to show you some information here that I would argue that in some cases it's dated, but that's okay, because what I'm going to do is I'm going to call up TerraView, and we're going to take a look at some of these definitions. So if we're going to talk about circuit breakers and fuses, overcurrent protection device, the first thing before we even get into that, I can't start talking about circuit breakers when we haven't defined what overcurrent protection is. So I'm going to call up Link. I'm going to look at the 2023 code cycle. 100. And I'm going to overcurrent protection. Overcurrent protection. Let's talk overcurrent first. So first we have to understand what is an overcurrent. And I'm telling you, some people don't get this right. So overcurrent is any current in excess of the rated current of equipment. Let's just look at that. So any current in excess of the rated current of equipment. So what is the rated current of equipment? You may have a panel board, which is a 1200 amp panel board. Any current that is in excess of 1200 amps would be considered an overcurrent. That could be what? Overloads. They could be temporary overloads. They can be ground fault currents. They can be short circuit currents. Any of those types of currents that are greater than 1200 amps, because that's the rating of the equipment. All right. So it says, and now it's all one sentence, but I'm going to just read the beginning over again. Any current in excess of the rated current of the ampacity of a conductor. Any current in excess of the ampacity of a conductor is the way is. So you have the rated current of equipment or the ampacity of a conductor. And remember, how do we determine ampacity? So to determine ampacity of a conductor, I got to go to chapter 3. And then I might have to, so ampacity of a conductor. So you have two things. Oh, this is cool. So if you think about, wow, okay. Oh man, it's dovetailing. I'm having an aha moment. I apologize. So you have a conductor, and I've had this discussion in the past. Remember in chapter 3, table 310.16, that's your ampacity of conductors. And you have the ampacity based upon the insulation, right? Whether it's a 90 C insulation or a 75 C insulation. So if we go to 310.16, I'm just going to do a search, and I'm going to search for 310.16, and I got to go to all of NFPA 310.16 ampacity of conductors. I'm going to click on that. That'll give me in the ballpark. And then I have the table. So, excuse me. So for example, say a 1-aught conductor. A 1-aught conductor with insulation types TW or UF, those are rated for 60 C. We know that a 1-aught conductor can handle 125 amps continuously all day, all weekend, all night. 125 amps. That's how much current that conductor can handle. A 1-aught conductor that has types RHW, THHW, THW, THWN, XHHW, XHWN, USE or ZW, which is a 75 C insulation. Copper, I'm talking copper in both cases, a 1-aught conductor can take 150 amps continuously. Every day of the week, 24/7, 365, twice on Sunday. 150 amps. Now you can have 90 C insulation. So any of the insulation types that are shown in this table that are for 90 C, that 1-aught conductor can take 170 amps continuously. Now, if you think of what's happening, the copper in the conductor, when you increase current through it, it heats. And the insulation, which is your material that's around the conductor, and sometimes it's thin, sometimes it's thicker. It will vary depending upon the types of materials that is wrapped around that conductor. You don't want to melt that insulation. You don't want to damage the insulation. And these currents are not short circuits. Okay, so you're not worried about annealing. You're not worried about vaporizing the copper. At this value, you're just worried about the heat that you're generating, and you don't want to damage the insulation over time. Okay, so that's what this table is telling you. So if I go back to the definition of overcurrent, and I type in overcurrent, C-U-R-R-E-N-T, and I would hope that you're following along in your code book. So we go to overcurrent, UV, any current in excess of the rated current of equipment or any current in excess of the ampacity of a conductor. And that's the ampacity. And the aha moment I had was, you know how we talk about, I can have a conductor that has 90 C insulation. If I land it on a termination that is rated for 75 degrees C, then I limit the capabilities of the overall circuit, not because the conductor can't handle the current, but because of the limitation of the termination. So when you take that conductor and you terminate it on a lug, if the lug and the equipment, not just the lug, if the equipment is rated for 75 degrees C and not 90 degrees C, I can always terminate a 90 degrees C insulated conductor in 75 degrees C equipment. I just can't use the 75 degrees C column unless I'm doing adjustment factors, right? So then there's a whole separate discussion on determining the ampacity of a circuit, not the conductor, it's the ampacity of the circuit, which includes the equipment now. So what an overcurrent is when you're exceeding that. So you may not exceed 1200 amps, but if you exceed the ampacity of that circuit, and this could be an improvement, because remember, the ampacity of the conductor, if I take a 90 degree C conductor and I say, well, it's 175 amps for 90 degree C column, but if I land it on 75 degrees C, I'm not giving you the ampacity of the conductor technically. I'm giving you the ampacity of the circuit. Just food for thought. Think about that. Do you agree with me? Is it really the conductor that you're determining the ampacity of, or is it the circuit because of the limitations of the equipment within which you're landing the conductor? Because what's the issue? It's about the heat rise in the equipment. I like it. So if I exceed that rating, then I'm into an overcurrent. And it says it may result from overload, short circuit, or ground fault. So an overcurrent can be an overload, it can be a short circuit, or it can be a ground fault. All three of those, any one of those is an overcurrent condition, as long as it exceeds the equipment. So if I have a ground fault on a circuit, say it's a 100 amp circuit, and I have a ground fault on a 100 amp circuit and it only pulls 5 amps because of the impedance, that is not technically an overcurrent, because I'm not exceeding the rating of any pieces of equipment nor the ampacity of the conductor. It can still be a ground fault, but it's not an overcurrent. Oh man, is that blow your mind or what? What am I saying that's wrong? I'm not saying anything that's wrong. So I can have a ground fault and it not be an overcurrent. Not all ground faults are overcurrents. Not all overcurrents are ground faults. There is an informational note. It says a current in excess of rating may be accommodated by certain equipment and conductors for a given set of conductors. Therefore, the rules for overcurrent protection are specific for particular situations. A current in excess of rating may be accommodated by certain equipment and conductors. So accommodated, meaning a current in excess of rating may be accommodated by certain equipment. Accommodated meaning it can handle it for a given set of conditions. For a given set of conditions. Maybe the conditions are that it's a short duration. Right? So I can have an overload on a conductor as long as it doesn't persist for, 24/7, 365. So short durations of overcurrents are permitted and don't do any harm because they don't generate enough heat. So a current in excess of rating may be accommodated by certain equipment and conductors for a given set of conditions. Therefore, the rules for overcurrent protection are specific for particular situations. This, I don't know about you, but I'm loving it. Okay, so that's an overcurrent. Now, what is an overcurrent protective device? So, an overcurrent protective device is, this is the definition of a circuit breaker. Okay, well, hold on. So now we're getting into another topic. Now we're going to talk about a branch circuit overcurrent protective device. All right. Tell me this isn't confusing, because I think it's confusing. I had a very hard time wrapping my head around this, and I don't know why. Sometimes I think I'm just a very literal person. If you tell me it's raining outside, I expect to have it raining. I don't expect overcast. I expect rain. So when you tell me a branch circuit overcurrent protective device, what would you assume? It is an overcurrent protective device that protects what? Service conductors, of course. Feeders and feeder conductors. I knew exactly that's where you were going. And it also, by the way, does protect a branch circuit. So a branch circuit overcurrent protective device, even though we call it a branch circuit overcurrent protective device, it protects more than just a branch circuit. It protects service, feeder, and branch circuits and equipment over the full range of overcurrents between its rated current and its interrupting rating. Now, an interrupting rating. What is an interrupting rating? I'm glad you asked, Robert from Omaha. So, an interrupting rating, Robert, is that value of current which an overcurrent protective device can safely stop from flowing. Let's see if it's a defined term. Oh my, what a concept. Let's look under I for interrupting rating. Insulating, interrupting rating. Here we go. The highest current at rated voltage. Why is that important? Oh boy, is that important. You need to know the voltage at which you're applying the overcurrent protective device, because if I tell you I have a circuit breaker that can interrupt 100,000 amps at 240 volts, that same circuit breaker applied at 600 volts is not going to be able to interrupt 100,000 amps. It's going to be something less. So as the pressure in the system goes higher, as the voltage goes higher, the interrupting capability of the overcurrent protective device is diminished. So keep that in mind. So you may see, and I had this happen to me one time. I did an educational session, and I made the statement about disconnect switches having a 10,000 amp short circuit current rating. And they said, oh no, that wasn't that, different topic. I had an inspector Actually, I had a contractor. You gotta love these. I had a design. I was a contractor or a design engineer, one of the two. Called me and said, "Hey, you need to call the inspector because they need to understand this. What they're saying is wrong." And I said, "What's the issue?" And he says, "I have one of your circuit breakers. It's a WWW whatever XYZ circuit breaker, and it has a 65,000 amp interrupting rating." I said, "Okay." And he showed me in the catalog, look, it says 65,000 amps. I said, "Well, yeah, I'm familiar with the breaker." And he goes, "I'm applying it on a system that has only, 50,000 amps of available fault current. And the inspector says my interrupting rating has been exceeded." And I'm like, well, I'd love to hear this one, right? So one thing I always remember, there's two sides to every story. So I called the inspector. And when I called the inspector, I asked him, I told him what's happening. I said, "I know you have a project. One of my circuit breakers is on there." And the engineer called me and said that, or the designer, whoever that was, called me and said that he's not misapplying the breaker. And you said the interrupting rating is being exceeded. I says, he's got a breaker that has the capability of interrupting 65,000 amps. So I don't understand. Help me understand. How does 50,000 amps of available fault current at a breaker that has a 65K interrupting rating be a misapplication? And he says, "Tom, this is at 480 volts. And I went, oh, immediately, because I don't have an interrupting rating at 65,000 amps at 480 volts. I have that at 240 volts, but I don't have it at 480 volts. It's a lower value." And that was a phone call back to the designer or engineer, whoever it was. And that was a difficult discussion to say, well, you misread the catalog, and there's a voltage in the columns and there is a voltage in the application. They both have to match. You actually are exceeding the interrupting rating of the circuit breaker. So that is a very important data point. Now, another thing I will say, that if you're looking at a trip curve like this line, this area right here is called the instantaneous pickup. That has nothing to do with the interrupting rating of a circuit breaker. Remember that instantaneous pickup is not the interrupting rating. The interrupting rating can be 10,000 amps. This is just where the instantaneous picks up. That's all that is. All right, so keep that in mind. If you're looking at a time current characteristic curve, don't call the instantaneous the interrupting rating. That will that could do a bunch of different things to you. So that would be ungood. All right, Mr. Tim Cernko taught me that word. Okay, and I'm not sure who taught it to him, but I'm just telling you who taught it to me. So, interrupting rating. So we talked about interrupting rating. We talked about the overcurrent, what an overcurrent is, what a branch circuit overcurrent protected device is. Let's see, what else? All right, so we know what a branch circuit overcurrent protected device is. I'm just going to go back to the definition of overcurrent protected device. Branch circuit, a device capable of providing protection for services, feeders, and branch circuits and equipment. So how does it protect equipment? I can have a circuit breaker feeding a panel board, and if it's a 100 amp circuit breaker, it means it'll only let 100 amps through, and it can feed a 100 amp panel board. Make sense? So I can't have a 60 amp panel board fed from a 100 amp circuit breaker, because now I can draw upwards of 100 amps through a 60 amp panel board, and that would be ungood. I would cause heating, and bad things can happen over time if you overload and overheat that equipment. All right, so an equipment over the full range of overcurrents between its rated current and its interrupting ratings. And I think that's how we got the interrupting rating. All right, so that is a branch circuit. Now, we had to define, here's, I think, one of the reasons why you have a definition for what a branch circuit overcurrent protected device is. And it's because of the supplemental overcurrent protective device. There is another term called overcurrent protective device, supplementary. And that's a supplementary overcurrent device. It's a device that's intended to provide limited overcurrent protection for specific applications and utilization equipment such as luminaires and appliances. This limited protection is in addition to the protection provided in the required branch circuit by the branch circuit overcurrent protective device. So you have a device, let me find it. Here we go. Excuse me. So you have a supplementary overcurrent protective device. And you'll notice what they look like. They're DIN rail mounted. Okay. So these devices are DIN rail mounted. They, as per the definition, they need to have an overcurrent protected device upstream providing protection for these. I had one time, I had an individual tell me that, you know, when you use a supplementary overcurrent protected device, I says, no, when? He says, when you don't need one. And I thought that was cute. But in any case, you still need an overcurrent protected device upstream. You will see these in industrial control panels and equipment in assemblies. They are covered by UL 1077. It's not a branch circuit overcurrent protected device, so you can't use it for branch circuit overcurrent protection. And they do resemble circuit breakers. Now, there are fuses as well that resemble fuses that are supplementary protection. So, and there's requirements around it. 240.10, supplementary overcurrent protected devices. Where supplementary overcurrent protection is used for luminaires, appliances, and other equipment, it shall not be used as a substitute for required branch circuit overcurrent devices or in place of the required branch circuit protection. All right? So, excuse me. That's what those devices are. All right. So that's your supplementary protectors. All right. So we know what an overcurrent protected device is. We know what an overcurrent is. We know what a branch circuit overcurrent protected device is, what a supplementary overcurrent protected device is. There was another one which is called a current limiting overcurrent protected device. This is a new definition in the 2023 code cycle. And this is a device that, when interrupting currents in its current limiting range, reduces the current flowing in the faulted circuit to a magnitude substantially less than that obtainable in the same circuit if the device were replaced with a solid conductor having comparable impedance. Which is not new. It was moved from Article 240, because I remember this definition, because I am more confused for having read it. There was a funny quote from a movie, but in my opinion, there is a definition in, I believe it's in UL 508 or UL 508A for a current limiting device, which I think is absolutely 100 times better than what this is. And you would think that I would put a public input in, and I have not. And it's probably because there are a lot of I'm in a target-rich environment. And, you know, like I said earlier, the code is like a fine wine. It just gets better with time. Love it. All right. So we know what a current limiting device is. And typically what a current limiting device is, and I'll draw this for you. So if we think about, boy, look at that, huh? When we think about a sine wave, and say, remember in a, what I should do is put this up here like this. When we think about a sine wave, so if this is the symmetrical sine wave, the asymmetrical sine wave during a fault, that first half cycle is a doozy. And then it does this, right? So, and you'll have the, they call that a DC offset. And that's based upon the X to R ratio. So this first hump is based upon the X to R ratio of the circuit leading to that. And what we mean by that, X is your impedance, R is your resistance. So you look at your impedance of the system looking back towards the source, which means you have the utility or generator, whatever is supplying the circuit, and you have all of the conductors, which if you look at the impedance values in chapter 9, for a conductor, it's a resistance and impedance, and an R and an X. And then you have, for motors, we are primarily X and very little if we ignore R. And transformers are as percent Z, but transformer X to R ratios do exist, but they're primarily X just because of the big iron core. They're very similar to motors. So we don't typically include the R. But I mean, but if you are an engineer who has a high level of focus on details, you may throw in the X to R ratio of a transformer to determine the R and the X instead of just assuming the percent Z is all X. So anyway, the X to R gives you that. Now, a current limiting device is going to do something. Remember, this is right here is one cycle. Right here is two cycles. And then if we drew this, right here is three cycles. So we have 1, 2, 3 cycles. And if you think about the instantaneous on a circuit breaker, you typically have around 2 cycles. What is one cycle? It is 1 over 60 or 0.016. 2 cycles is 0.032. And 3 cycles is 0.048. Is that right? Add 16, 4, 8. Yes. So 0.048. And remember, on a time current characteristic curve, when we draw this, we start at 0.01. So this already starts just a little bit over. So if I drew a circuit breaker like this, if this is 0.01 and this is 0.02, right? So you have 0.032 as 2 cycles, 0.016. So if this was clearing at 0.02 seconds, you're somewhere between 1 cycle and 2 cycles for 0.02 seconds, because 0.016 is 1 cycle and 0.032 is greater than 0.02. So that means you would have, for an instant, if you're in the instantaneous region of this circuit breaker, then you would have 1 cycle. There's your 1 cycle. And you would have, let's see, 0.032. So let's do this. 0.02. My calculator is right there. Do the math. Let's do math together. What is 0.02 divided by 0.016? Divide. It's 1.25. So 0.02 seconds is 0.02 seconds is equal to 1.25 cycles. So 1 1/4. So this is 1. I'm going to do, let me do this. I'm going to highlight in red or yellow. This is 1 cycle, and 1/4 would be right here. Right? So for that circuit breaker in its instantaneous region, we could do this. Right? So that is the waveform that would flow in the instantaneous region. If the circuit breaker was current limiting, then what you would have is, let's use a different color. Let's use blue. Your current would come up and then go down. Right? So now a fuse is going to be much faster than a circuit breaker. It's just physics. So a fuse will clear faster than a quarter of a cycle. So 1/4 of a cycle is equal to 0.016 divided by 4. So 0.016, well, 0.016 divided by 2 is 0.008. Divide that by 2 again is 0.004. 0.004. 4 milliseconds. Think about that. Think about how fast that device is. So that is a current limiting device. And what you will typically see if a circuit breaker or a fuse is current limiting, you're going to see a symbol that looks like this on the breaker or the fuse. Well, breakers, they put them on breakers. I'm not sure. I think they just say current limiting on fuses, but you may see that symbol. But in any case, that's what we mean by a current limiting overcurrent protective device. And remember, the current has to be high enough to be in the current limiting region. All right, so we're only 41 minutes into this discussion. And what have we learned? Well, we've learned about overcurrents. We've learned about a branch circuit overcurrent protective device. We've learned about, we learned about overcurrents, branch circuit overcurrent device, supplementary overcurrent protective devices, and current limiting overcurrent protective devices. We talked about, you know, that there are fuses and circuit breakers that are current limiting. We do know that the fuses will operate faster just by physics, but they're both going to operate fast. We know that we talked about overcurrents, being ground faults, short circuits, etc. All right, so let's go back. Let me just go back to my discussion points. So how do I do this? I talked about all of those different. Okay, now let's talk about the types of circuit breakers that you're going to see in the marketplace. So you're going to see molded case circuit breakers, insulated case circuit breakers, and low voltage power circuit breakers. So a molded case circuit breaker is a circuit breaker that is assembled as an integral unit in a supporting and enclosing housing. Oh, let's do this. You see what that says, right? So I'm going to leave that up, and I am going to go to the 2023 code. I'm going to look under circuit breaker, because I can. What is a circuit breaker? What is a circuit breaker? Circuit breaker. Child care facility circuit breaker. So these are the terms. So there is a circuit breaker adjustable, circuit breaker instantaneous trip, circuit breaker inverse time, and then circuit breaker non-adjustable. So there are, and then there's circuit breaker. So let's look at just the definition of a circuit breaker. The 2023 code says a device designed to open and close a circuit by non-automatic means and to open the circuit automatically on a predetermined overcurrent, there's that word, without damage to itself when properly applied within its rating. Now, when we say within its rating, what are the ratings of circuit breakers? We know that a circuit breaker will have a continuous ampere rating, okay? And now molded case circuit breakers will have a continuous ampere rating anywhere from 15 amps to 2,500 amps. And actually, we know this goes to 10 amps because of the 2023 code changes, okay? We know that another rating is the interrupting rating, and we also know a voltage, and we know a frequency. So all of these are ratings. We have We have the frequency rating of the breaker. We have the voltage rating of the circuit breaker. We have the current rating of the circuit breaker. We have the interrupting rating of a circuit breaker. And what a circuit breaker definition is: a device that's designed to open and close by non-automatic means, meaning you're opening and closing it either with your hand on the handle or maybe a mechanism, and to open the circuit automatically on a predetermined overcurrent. So it should say open the circuit automatically based upon a predetermined set point of current. It's not a predetermined overcurrent. Or is it? An overcurrent is a current in excess of a rating of a conductor or equipment. And the predetermined overcurrent would be when the current exceeds that value. So you would set, I get it. I get where they're going. You're setting the set point for, say, a 1200 amp panel board. If you're feeding it from a breaker, the set point has to be set at 1200 amps. I'm good with that. Without damage to itself. That's the unintended rapid disassembly in the field when properly applied within its rating. There is an informational note. The automatic opening means can be integral, direct acting with the circuit breaker, or remote from the circuit breaker. What does that mean? Well, that means that I can have things like electronic trip units, right? And that was when they married. So if you look at something like this is an electronic trip unit that is on a circuit breaker. So this is the circuit breaker, but then the trip unit itself, in this case, it's a part, it's down below on the bottom of the circuit breaker. But in some cases, that trip unit might be on the side, but now it is separate. Well, I guess it's still technically a part of the circuit breaker, right? So it says the automatic opening means can be integral, which this would be integral even if it's an electronic trip unit. Direct acting with the circuit breaker. This would be direct acting with the circuit breaker because there's a plunger here, and everybody does it different, but there's a plunger here that tells this mechanism to open, and there are CTs, there's donuts in here. And I know I'm getting hungry, I'm mentioning donuts, and the current passes through this and it comes out the bottom. Okay, and that the sensor technology that's in there is what's used to determine the amount of current that's flowing, and then we program a set point. Okay, but now you could, for example, have, so this is a shunt trip, so you could have another device external, and you could have a set of CTs. And this brain basically says, I'm going to take the CTs, and maybe the CTs are up here, or maybe the CTs are down here, and they come into this device, and then the brain says, oh, you know what? I'm going to tell this to trip through this type of a shunt trip device, and there's little wires that go in here, and all of a sudden you are tripping this breaker remotely from the circuit breaker itself. All right, so the circuit breakers can get, it's complicated. All right, so a circuit breaker is a device that's going to open. If you think about the mechanism, like the construction of a circuit breaker, you have a frame. This is let's do this. Let's go back. These are the three types that you're going to see on the market: a molded case circuit breaker, an insulated case circuit breaker, and a low voltage power circuit breaker. Now, I will say that an insulated case circuit breaker is not a technical term driven by a code or a standard. It's a marketing term. They needed a way to define a larger molded case circuit breaker. Both of these devices right here. Well, look at that. It's a nice rectangle. Both of these are listed to UL 489. Okay, both of those are listed to UL 489. And this is your power circuit breaker. Now if I, which is a much bigger beast, right? So here's the interesting part. Okay, we already talked about all this. Now, ignore the frames. Okay, all of this here, ignore all of these because every manufacturer calls it something different. This is just one manufacturer's way of doing it, and, at least identifying the frames. But what this shows you is that, look, I can buy a 200 amp frame breaker here, right? I'm going to highlight it in yellow. I can buy this as a 200 amp breaker. I can buy this as a 200 amp breaker. I can buy this as a 200 amp breaker. I can even get this as a 200 amp breaker. So these are the 4 frames that you can purchase from a manufacturer. And you'll notice the number gets larger over here. This can go up to 600 amps. This can go up to 400 amps. This can go to 250. This could go to 225. But I can buy a 200 amp breaker in any of those frames. And they get larger, physically larger. Now, why? Why would I buy, I'm going to call this A, B, C, and D. Why would I buy breaker D for 200 amps, for a 200 amp circuit, which is going to be a bigger breaker, it's going to be a heavier breaker, it's going to be a more expensive breaker? Why wouldn't I buy a 200 amp breaker that is in the A column, which will be, it's got a 225 amp frame. You can physically see in the pictures it's smaller, and it's probably going to be cheaper. And I'll tell you why. The larger the breaker, when I look at the instantaneous capabilities, okay? So if I go back to this and I look at the trip curve, that 600 amp breaker might look like this. And obviously I'm not accurate to what the actual curve is. I'm just going to give you Tom's creative time current characteristic curve. So let's say that this is the 600 amp frame breaker that can go to 200 amps. Okay. And we're going to say this is 200 amps. All right, so there's your 200 amps. The 250 amp frame breaker may do this. And the instantaneous value is less. Why is that? Because the contacts inside of this circuit breaker, for the 250 amp frame, the contacts will hold its contacts closed up to the instantaneous region, right? You exceed the current for the instantaneous pickup, and then they're going to open. The 600 amp frame breaker that can be dialed down to 200 amps and lock the cover, right? All that jazz, and from 240, Article 240, the instantaneous will be higher, meaning I can have higher currents. And my contacts will have to stay closed longer than on the 250 amp frame breaker. And how do I keep my contacts closed longer? Think about this. The hard part for a circuit breaker is not opening the contacts. The hard part is holding the contacts closed under all of those magnetic forces, wanting to move these contacts apart, and you're going to get chatter, right? The chatter is going to create dimples. It's going to create heat. You do not want your contacts to chatter. So you want how do I keep these contacts closed under more magnetic forces? I put beef on the job. I bring Lou Ferrigno to the job, or Arnold Schwarzenegger to the job, and I make sure that I have bigger springs, I have bigger arms, I have a bigger mechanism, which means the breaker will have to be bigger to hold those contacts closed. And then if the breaker is larger, I may not be able to fit it into a panel board that the smaller breaker will fit into. So there's another dynamic. So picking this circuit breaker, you're going to pick it based upon its ratings, whether or not you need the contacts to be closed longer. Like, why would you care? It will be application driven. If I'm on the line side of a transformer and my inrush currents are high, I might need to have a frame breaker that has some instantaneous at a higher value and dial down. If I have motors with inrush currents, many motors that are going to be starting, I may need an intentional delay upstream, meaning I'm moving the instantaneous to the right, adding an intentional delay, keeping the contacts closed longer to let the motors start. So there are many different reasons why I may pick a larger breaker over a smaller breaker with the same amp rating, and it will be driven by the application. If I have an existing panel board, right? And let's say that you have an existing panel board and it's a larger panel board, and you look at the manufacturer and the manufacturer says, well, I can put, or you can put breaker C with a 400 amp frame, but you can't put breaker A in this panel board, and you need 200 amps. Guess what? You're buying breaker C, even though it's going to be more expensive. But what would be even more expensive is if you have to add another panel board to be able to take breaker C. Not all panel boards, for example, a residential panel board, isn't going to take any of these circuit breakers, period. None. It will take a specific circuit breaker. That's why on the panel door, we put a guide that tells you what breakers go into those panel boards. Make sense? So that's what is that's why you'll have these different, that's a molded case circuit breaker. Molded case circuit breakers go all the way up to 2,500 amps. Now, insulated case circuit breakers, we said this is still a UL 489 device. It's a molded case circuit breaker. If you didn't remember, insulated case circuit breaker, ICCB, is a marketing term. It's a way to differentiate this hand mechanism type of device from the smaller molded case circuit breakers. And they needed to come up with a catalog number system, and the industry sort of settled on using insulated case circuit breakers for whatever reason. I'm not going to go back in history to understand why. I really don't care. Do I like it? Absolutely not. It's a UL 489 device. That's my personal opinion. I think it adds confusion. I don't like to add confusion when we're already confused with everything else that's going on in this world, right? So, but I can't change that. What I can do is help you understand the difference. An insulated case circuit breaker, what sets it's different from the other molded case circuit breakers, because it is a molded case circuit breaker, just not a, we just call it an insulated case, is this handle. It's got a charging mechanism. It's got a charging bar. It has buttons to turn it on and off. It'll have a charging mechanism to close the mechanism in. It goes up to 6,000 amps, down to 800 amps. So would you rather buy an 800 amp one of these or an 800 amp one of these. Why would you buy this breaker in 800 amps when you can get this breaker at 800 amps? And I'm telling you, just from the looks of it, I know which one's more expensive. The reason is the application again. It's, do you need those contacts held closed longer? If you have this circuit breaker at 800 amps, your instantaneous is going to be way over there on the right. You're probably going to have a delay. It's going to be an electronic trip unit. I'll tell you exactly. I'll tell you what this time current characteristic curve is going to look like. Just like this. It's going to be an electronic trip unit. You're going to have the long time pickup. You're going to have your long time delay. You're going to have your short time pickup. You're going to have a short time delay. And then you're going to have the instantaneous. And this region right in here, right in this region, that's the contacts being held closed for up to 30 cycles. That's a long time to hold its contacts closed for thousands of amps. A lot of magnetic forces. Why would you need that? And where would you see that type of a breaker? Up closer to the service would probably be a good guess. Because you're further up into the system, you want that device to hold its contacts closed while all those little puppies downstream do their job and open things up. That is what that device does. And that's why you'll see the insulated case. And then you go to a power circuit breaker, and I call a power circuit breaker is your Swiss watch of circuit breakers. I mean, these are big beasts. You're not going to carry it into a room. You're going to wheel it in on a dolly. It has interrupting ratings up to 200,000 amps with current limiting devices inside, current limiting fuses, or they call them current limiters. They don't call them fuses. 800 amps to 6,000 amps, and you'll find these in switch gear, right? You're not going to find this in a panel board. It's not going to fit in a panel board. These are going to be in switch gear. These are going to be in switch boards, and these are going to be in panel boards. So that's sort of the gist of how your overcurrent protective devices, branch circuit overcurrent protective devices, current limiting overcurrent protective devices, how they're constructed, and some information about how they're properly selected, making sure that you have to understand the application and how they're used. So I've been going for an hour. I've been talking for an hour, and I know this program is only an hour, and I gave you a little tease of overcurrent protective devices and overcurrent protection. I hope you got something out of this session. I am sorry I'm not able to be live today, but this is a recorded session, and I hope that you were able to chat it up, because I will hopefully be watching on my phone while I am in a meeting, which I probably shouldn't do because I should be paying attention to the meeting. But I'll try to peek into this event and look at some of your comments and see if I can contribute myself. So hopefully you got something out of today. I really appreciate your time. I appreciate you very, very much so. I thank you for watching the channel, following the channel, subscribing to the channel, hitting the thumbs up. And if you're an IAEI member out there, thank you for your membership and your commitment to the electrical industry and electrical safety. And if you're not an IAEI member yet, please consider it. It's a great organization, some great resources for you. We have a magazine, there's discounts on educational materials, and you get to see my lovely face every Tuesday. So anyway, thank you for everything. Thanks for hanging in there for an hour. I hope you enjoyed it. Remember to take care. Remember to take care. Stay safe. I'm hitting the buttons all over here. I've got my hand right by this, and I'm touching my buttons. Look, see. These are the buttons. This is called a Stream Deck, and if you click on these, if I click this, it's teach. If I click this, it's me. So that's how I navigate. So if you ever wanted to know, it's called a Stream Deck. It's a great little tool. So in any case, I am going to try not to touch the buttons. So, all right, one last try at saying goodbye. Thank you for what you do for the electrical industry. Thank you sincerely for what you do for electrical safety. And remember to please stay safe and please stay healthy. We will see you next week right here on this channel. Until then, signing off.